second application of your Biot-Savart law is nothing but a force acting between parallel current carrying conductor. So here I have drawn two conductor, conductor 1, conductor 2. Conductor 1 carries a current I1, current 2 will be carrying current I2. Both the conductor have a length L. They are separated by a certain distance which is equal to E. And now we are going to concentrate on the force concept. So what we first think, this is the first conductor through which current I1 is flowing. So due to flow of this I1 current, there will be a development of magnetic field surrounding to this first conductor. So at A distance, if I locate any point P at the A distance, then this A point, P point will be at a distance of A. So due to flow of this current I1 through first conductor, at P point there is a development of magnetic induction, which just you have seen in the previous derivation, which is equal to nothing but mu 0 I upon 2 pi r. So now this magnetic field will be developed at this P point. That is magnitude. Now we can think about the direction. Now what is the direction here? This conductor, if I hold in my right hand, so outstretched thumb gives us the direction of flow of current, and curled finger around this conductor will give us the magnetic field. Means direction of magnetic field at point P is inside. So this inward arrow will indicate the direction of magnetic induction, B1. Now I can concentrate on the second conductor. This second conductor is like a chalk. So this chalk will act as a second conductor. Current will be flowing through this second conductor in the upward direction, and magnetic field acting on the second conductor B1, which is inside the plane and perpendicular to its length. Therefore, this second conductor will experiences a force F2, which is nothing but your I, L, B. But current flowing is I2, length is L, and magnetic induction experienced is B. Now, flow of current is in the upward direction, magnetic induction is inside the plane and perpendicular to length. So now what will be the direction of force? So for that purpose we are going to use the Fleming left hand rule. Now what Fleming left hand rule says that? Fleming left hand rule says that if I am saying that your direction of current is upward, so your forefinger indicate direction of current, middle finger indicate direction of magnetic induction, and force will indicate, this thumb will indicate the direction of force. So now I will rotate my left hand and I will turn in this manner. So your current will be in the upward direction, your magnetic induction is inside. So your direction of force will be towards the first conductor. So direction of force F1 will be towards the first conductor. Now we can think about this second conductor. Now I say that current flowing through this second conductor is I2. I can locate a Q point. This Q point is at a distance of A from the second conductor. So due to flow of this current I2 through the second conductor, the production of magnetic field at Q point I can say as a B2. This B2 I can write down as a mu 0, then current flow is I2 divided by twice by R. Now this B2 direction, when current will be flowing upward, the direction of B2 which will be developed at Q point is outside. So now your current is in the upward direction, magnetic field is outside. So now due to that, this second conductor experiences a force F2 which will be towards the first conductor, and this F2 force experienced is nothing but towards the first conductor. So that force F1 I can say that which is equal to F1 force is experienced by the first conductor due to flow of current I1, due to length L, and due to magnetic induction, which is equal to V2. Means now I am getting two forces, F1 and F2. Now that force F1 and F2 I can rewrite by substituting values of B1 in the expression of F2. This B1 magnetic induction is due to current I1. So now instead of place of B1 I can put the value which is equal to mu 0 I1 upon twice pi R. And in the place of F1 force I can place the value of V2. This value of V2 is what? Mu 0 I2 upon twice pi R. Now if you concentrate on F2 expression and F1 expression, both the expression consist of same terms, and therefore I can write down that your F1 force is equal to F2 force, which is equal to some force F can be written as, now concentrate which terms will be there. Mu 0 term is everywhere, I1 I2 term is there, so I1 I2 into L divided by twice pi R. Here R is the distance. Now here distance between the two conductor is nothing but A. So I can replace this by. So now I am getting this force. So this force F by L. This L term I will take it for the division. So force per unit length, which is nothing but F dash, can be written as a mu 0 I1 I2 upon 2 pi A, where A is nothing but the distance between two conductors. So in the previous expression, that R distance we have replaced by the E. So this is I am getting as a force per unit length of a conductor. Now from this force per unit length of the conductor, I can give the definition of 1 ampere current. Now how I can give the definition of 1 ampere current? Just concentrate here. I can consider current I1, which is equal to current I2, which is equal to 1 ampere, when your conductors are separated from each other by distance of 1 meter. So if this value of I1, I2 and A I am going to substitute in this F dash value. So your F dash will be, now I can say this F dash I can write down as a mu 0 I1, I2 is 1, so it is multiplied by 1 divided by 2 pi, and A value is also equal to 1. So what I am getting this F dash value, I will get it as a F dash is equal to mu 0 value is 4 pi into 10 raised to minus 7 divided by 2 pi. So this 2 pi will get cancelled with 4 pi as a 2, and F dash value I am getting as a 2 into 10 raised to minus 7, which is force per unit length, that is Newton per meter. And now using that data, I can give the definition of 1 ampere current. The current is said to be 1 ampere if the force per unit length experienced between two conductors will be 2 into 10 raised to minus 7 Newton per meter when the conductors are separated by distance of 1 meter. Now here in this conductor, two conductors are parallel, current directions are same. Therefore F1 and F2, both the forces are towards each other. Means if the flow of current is along the same direction between parallel conductor, so nature of the force is attractive. But if the current directions through these conductors are opposite, means one is moving upward, another is moving downward, so the force experienced by both the conductor is away from each other. So that type of force is nothing but the repulsive force. So this is nothing but your second application of Wagner's law. Thank you.